Hey, it's Alan, and this is Newton's method. Almost done with this chapter, continuing on with another namesake, Sir Isaac Newton. Now, this guy was not French, finally, right? This fellow was English. And so what he came up with was a pretty cool way. Now, this is way before calculators, so we call it an iterative or repetitive process that allows us, before there were these calculators and computers, to find a zero or root, x-intercept solution to a function without using any of those fancy techniques or technology. So again, a little bit different way, something that we won't use a ton of. So go through this pretty quickly because there's really only this in this section. So Newton's method, begin, is for when we are finding a zero, which means we're looking for that value, that constant that makes our function equal to zero, hence the name. And what he discovered was that we could closely approximate, you can do this as many times as you have the patience for, using an equation of the tangent line to our function that we are given and finding where it crosses the x-axis. Again, remember we call that the x-intercept, zero, solution, root, all those different things. And if we keep repeating that process until we figure out, hey, this is starting to actually get really, really close to what we've been finding the last one or two times that we've tried, then we'll go ahead and stop there and say, hey, this is as close as we can get it. And here is what it is. Now, I know this doesn't look like much yet, but remember, we're trying to find some x that gives us our function, zero. I'll explain what it is, but yeah, it's pretty simple, pretty beautiful, because there's just three parts to it. And these will never change. Of course, they'll change as you continue the process, but the order of these things will never change. This will always be, if you're trying to find the next iteration, so n plus 1, then this was the previous answer that you just came up with or started with, is this that we are going to plug into our function, as is this that we are going to plug into the derivative of our function. Okay, so just a little bit different format, and let me hopefully make it make more sense with the graphical explanation, a visual, if you will. So let's say we had our actual function, our curve here. We're going to call that f of x. Let me zoom in a little bit here. So we got our original function, f of x here, and we got some tangent line. So let's say, all right, we can see that it goes through at this, and that's what we want to find. All right, but we're going to start by picking some value that we do know, some nice value. Okay, let's say it's a 2. Well, then I can plug in and find my 2 into my function and find the y value. Now, of course, with that, then I'm going to find the slope of my tangent, aka the derivative. And what we're actually going to find by doing all of this and rearranging that y minus y1 equals rm times x minus x1, we're going to rearrange some of this stuff in order to find right where that crosses. And then what are we going to do with that? Well, we're going to hit the reset button and we're going to do it again. Now, instead of finding this value and doing the derivative, slope of the tangent, and finding where that crosses through, where it's equal to 0, then we're going to now take that value and we're going to find its derivative and where that crosses through. And that's going to get us closer and closer and closer. You can see this whole limit process again, which remember is all a derivative is, that we'll get so close eventually, depending on how many times we decide to do this, to the actual root solution or x-intercept. Now, hopefully that makes a little bit more sense via a graph, but ultimately you just got to do it. And because this is so different, I'm going to do two examples with you guys. And here's the first. Now I'm giving you the function y equals x squared minus 3x minus 3, which you all should know looks like a parabola. And I want you to find the two places where this would equal 0. Now, of course, if we could, we would try to just factor this. But as you can see, this doesn't factor because nothing multiplies to 3 other than 3 and 1. And those are, no matter how we put our signs, going to combine to a -3. So we can either use completing the square, which is not going to be very nice because of our b term being odd, or what most people would decide to use anyways, quadratic formula. And that would give us our two roots. But I just want to show you a different way. I'm going to circle back to that in just a minute. So what is Newton's method? Remember, it stated that if you're trying to find the next x along that x-axis, then you need the one before it. So if you don't like n plus 1, you can just call this n and then just put n minus 1. They just didn't want to have to put that 3 times, and they only put it once. I know, mathematicians, lazy, right? So we got our initial thing, which they're giving us one. I'm going to show you how to find out where this would be about by showing you the graph of this. But then we will just subtract the fraction or ratio of that thing plugged into our original function and that thing plugged into our derivative of our original function. So let me quickly show you by going to Desmos that if we graphed our y equals x squared minus 3x minus 3, as you can see there, that's what I've graphed. If I zoomed in on the two places where this thing, my y value, my function, would equal 0, you can see if I zoom in there, it's pretty close to 4, or if we wanted to go to the negative, pretty close to -1. But what if we didn't have these capabilities? Should we know how to graph this on our own? Sure. Without any technology, most definitely. And could we see that it gets really close to 4? Hopefully. So then we can choose a value that's really close to one of our zeros and then decide that that's where we're going to start this Newton method iterative process. Okay, so let's do a couple of these and see if we can't approximate to 4 decimal places. Now, in order to start this, remember we're going to need both the original function and the derivative. So I'm going to start by just taking the derivative, which should be super easy. And now I got both of those things actually stacked up the way that I should. And then now I'm going to start by using my Newton's method in first value of 4. So just to show you what it would look like, I'm replacing my n's with 0 to start. So what I'm actually finding with this first iteration is x sub 1. We say subscript, so x sub 1 or x1. That means I can now substitute in what I know x sub 0 is, which is that 4 there, there, and there, to my two functions and its derivative. So that would give us, when we plug the 4 into here, and of course, obviously there. Now we just got to clean this mess up and then do the subtracting, which I'm going to need a common denominator. So multiplying by my fancy 1, I get 20 over 5 minus 1 over 5. So we just found x1 to be 19 over 5, which if you'd rather use the decimal form would be 3.8. Now I say use the decimal form. Is that our answer? Well, we know it's pretty close to that. Somewhere between 3.5 or 4 when we looked at our graph. And if I kept zooming in, you can see actually, yeah, just doing one iteration, it's really close. But what if we kept zooming in? We could figure out what it is even more if we did another iteration of it. So let's do it once more, but now using this x1 that we just found to find x sub 2. So when I rewrite using this same original format of Newton's method, I'm now going to use my n as 1 because we now have that. So that's now what we're plugging in. So we got x of 1 plus 1 for our n. So we're actually finding x2, which means we're going to plug in x1 everywhere from my original and then my derivative function. In doing that, remember, we're going to now use the 3.8 everywhere for our x1. And in doing so, we would get these, obviously the x1, but then plugging it into our original and our derivative function would yield these two values, and then dividing, cleaning this up, would give us an x2 value of, and remember, the namesake down here is how many iterations you've done to get that 0 or that x. And since it asked us to find or approximate the root to 4 decimal places, we would go 1, 2, 3, 4 and look at the 5th and see that we would keep it there. So our final answer would be pretty close to what we got the very first iteration. Now let me make this all make sense for you. Hopefully you understood Newton's method and the whole process, but remember what we were trying to do was basically solve our y equals x squared minus 3x minus 3 quadratic function for when it was equal to a y of 0. And if we did the quadratic formula for this, here's what we would get. And if you notice that we actually get really, really close to, if we did it to 1, 2, 3, 4 decimal places, just like the other one, we would have had our 3 there, just like we would have here. It would have actually given us the exact same answer. Now, of course, this one also gave us the other that we saw, but looking back at our graph, you can see that we found that 3.79-ish pretty darn close. So that's one way to use Newton's method. The second way, also similar to what we are going to do here, of course, we are going to use Newton's method, so that function as many times as we want or need to. This time, what the approximate of the square root of 3 is. Now, if you've ever wondered how to figure that out without using a calculator, this is how they did it way back when. Pretty creative. Let's take a look at it by creating a function that would give us this value. And then we're also going to find what we would start with by using a little thing called the squeeze theorem. Now, the first thing that we got to figure out is what kind of function would we be using in order to come up with this as a solution. And if you think about it, we want to figure out y equals what. When we let that be 0, can we solve and get a square root of 3? And if you come up with x squared minus 3, excellent, well done. Add the 3 over, take the square root, you would see that we would get a square root of 3 and a negative square root of 3, but we're just looking and focusing on this one for now. Then what would be a suitable starting place? Well, give me some roots that you know around it. And that's what I mean by squeeze. If you are tasked with finding the square root of 3 and what it is about, I know you can reach to your calculator, hit a couple of buttons, and it'll do it all for you, but this is actually what it does, like that. This whole Newton's method iteration process. And what would we know really close to this? Well, we know our answer is something between 1 and 2, and probably closer to 2 because 3 is closer to 4 than it is 1. So that's what I meant by squeeze. Squeeze it between two things you know to see what you don't know. So we can guesstimate it'd probably be 1.8-ish, 7, however many decimals we want. We could try to figure it out, but now we have the tools that we need. And we will go ahead and call our x sub 0 a 2 for our y value, our function that we're trying to get this whole thing to be. Right? And again, if you plug in 2 here and square it, you get 4 minus 3, which is 1. We're trying to see where the y would equal 0. So here's the setup, again, just one way for this value. And now we will use that Newton's method again a few times just to kind of get an idea of what it looks like. And because I'm going to have to use this, which uses the original function that we came up with and its derivative, now I have everything I need. We've got a value that we think is going to be a good starting place that will get us close to 0. And we will continue until we feel like we've done it enough. It's repeated, or however many iterations they ask us to do. So plugging in our x sub 0, our starting place, to get our first iteration, we get the 2. 4 minus 3 is 1 on top. 2 times 2 is 4 on bottom. So multiplying by a fancy 1 to get our common denominator, we'll end up with 7/4, or 1.75. Now go ahead and pause it here and try to do the second iteration on your own if you're feeling comfortable, and then I'll walk you through it once more. All right, so hopefully you were able to get somewhere with this quickly, rewriting it as our x of 1 plus 1 for our x1 now, so that we can find our second iteration. We would now have our 1.75 everywhere we had that x1, and that gives us, combining like terms, we get, now here's the funny thing, a lot of you are getting these by using a calculator. Now remember, if we just wanted to know what the square root of 3 was, couldn't we just plug that into our calculator and get out the approximation? So do me a favor, go ahead and do that and see after just 2 iterations how close we are. And if you want to take it further for practice, by all means do. Otherwise, you guys now have the gist of it. But plugging that into our calculator, you should have gotten 1.732. And if we went to the 4th decimal place again, we would have rounded up to 1. And that's exactly what we would have had here. The exact same value in just 2 iterations. Pretty ingenious. Nice little tool for us to be able to do things by hand, but because of the advances in technology, we don't have to do this anymore, thankfully. That's all I got for you. Take care. I'll see you guys. One more section left in chapter 4. We're almost there. Keep working hard and practicing this stuff until you master it. Until the next time, Coach Allen, signing off.